Hello everyone and welcome to the next video in the series. This is a technical skills video on the topic of multiplication and division of decimals. And we begin with multiplication. Now, to explain how multiplication works, how the algorithm works, there is a key concept that you should know, and this has to do with the effect of the movement of the decimal point on the size of a number. So as an example, if we move the decimal point in 14.253 forward over one digit and bring it between 2 and 5, then the size of the number changes. In fact, it becomes 10 times larger. And if we go from 142.53 to 1425.3, where the decimal point has moved forward over one digit again, makes the number 10 times larger again. So every time you move the decimal point forward over one digit, the number becomes 10 times larger. The reason for this is because when you move the decimal point, you reassign the value of each of the digits. As an example, going back to the numbers that we have here, 14.253, 142.53, 1425.3. I've lined up the decimal point in them. And initially it was between 4 and 2, and then it moved forward over one digit to between 2 and 5, and then again we moved it forward over one digit to between 5 and 3. Now comparing 14.253 and 142.53, you notice that the value of each digit has become 10 times larger. So the one here, which was in the tens, is now in the hundreds. It went from being a 10 to being 100, and so its value became 10 times larger. 4, which was in the ones, is now in the tens, and the value of 4 became 10 times larger. 2, which was in the tenths, is now in the units, and its value became 10 times larger. Think of 2, if you think money, the 2 refers to 2 dimes, and the 2 here refers to 2 loonies. And of course 2 loonies are 10 times larger than 2 dimes. And same thing with the 5. It was in the hundreds and now it's in the tenths, and so its value became 10 times larger. And same for 3. So because the value of each digit becomes 10 times larger, by the distributive property we can conclude that the sum total becomes 10 times larger. Okay, so 142.53 then is 10 times larger than 14.253. And 1425.3 is 10 times larger than 142.53. This means that 1425.3 is 100 times larger than 14.253, because we get 10 times 10, which is 100, not 10 plus 10. Each time you move the decimal point, you make the value 10 times larger. Alright, so what we have now is that if you move the decimal point forward over one digit, the number becomes 10 times larger. If it moves to the right over 2 digits, then it makes the number 100 times larger. Moving the decimal point to the right over 3 digits makes the number 1,000 times larger, and so on. We can go the other way. If you move the decimal point back over one digit, you make the number 10 times smaller in size. If you move the decimal point back over 2 digits, it makes the number 100 times smaller in size. And 3 digits will make it 1,000 times smaller in size. Now, all of this has to do with that one feature of decimals that is so central to explaining how decimals work. And this notion, which I introduced in the first video on decimals, has to do with the fact that each place value is 10 times larger than the one on its right, and 10 times smaller in size than the one on its left. Alright, next we have the multiplication algorithm. And I'm going to list the steps here and go through them once, and then I'll explain using examples how it is that it works and why it is that it works. The steps are: drop the decimal points in all of the numbers that you are multiplying. Then multiply the resulting numbers without their decimal points. Find out how many decimal digits you started with. Make sure you end with as many decimal digits. Okay, example 1, 0.23 times 0.7. So what we have is, on the right side, I have 0.23 times 0.7. Step 1 says drop the decimal points in both numbers, and therefore we end up with 23 times 7. Step number 2 says multiply the resulting whole numbers. So we multiply 23 by 7. 7 times 3, 21. 7 times 2, 14, plus 2, 16. And now, in order for us to find out what the answer to the original problem is, we count the number of decimal digits in the given numbers. We had 2 here, 1 here, for a total of 3. Recall that decimal digits are digits on the right side of the decimal point. So we start with 3 decimal digits, and we should end with 3 decimal digits. So 161, we can place the decimal point just before the 1. In effect, we end up by putting the decimal point here, we'll end up with 3 decimal digits. And we also always prefer to put a 0 before the decimal point in case the whole part is 0. And therefore the answer to the original problem will be 0.161. Now, to explain how it is that works, let's take a look at the top number. In going from 0.23 to 23, we have made the number 100 times larger. This is because the move is the same as taking the decimal point from where it is and moving it forward over 2 digits, and that gives me 23. And because we just mentioned that if you move the decimal point over 1 digit, you make the number 10 times larger, moving the decimal point from here to the end makes the number 100 times larger. 0.7 becomes 10 times larger when we drop the decimal point. And again, that's because it's the same as moving the decimal point forward over 1 digit. And that makes the number 10 times larger. Now, if the top number becomes 100 times larger and the bottom number becomes 10 times larger, the result of the product will be 1,000 times larger. And therefore, to find the result of the original multiplication, we have to divide 161 by 1,000. And that would be the same as moving the decimal point back over 3 digits. And that gives us 0.161 as the answer. Now, of course, the 2 zeros in 100 come from the fact that we have 2 decimal digits, and therefore we move the decimal point over both. The 1 0 here corresponds to the fact that we have 1 decimal digit, and the 3 zeros here will translate into 3 decimal digits. So instead of going through this kind of argument all the time, we begin by counting the total number of decimal digits. That tells us how many times the product will be bigger. 1,000 times. And then make sure that we make the answer 1,000 times smaller from what we have here. All right, problem number 2, 2.6 times 3.18. And so in this case, if you multiply the numbers, you'll end up with, if you multiply them without the decimal points, you'll end up with 8,268. And then because we have 3 decimal digits to begin with, those are the digits 6, 1, and 8. We need 3 decimal digits at the end, and we get 8.268. Next, we have 0.0024 times 17, which comes to 0.0408. Let's see how. Now, in this case, we begin by dropping the decimal points, and so we end up with 24 times 17. And then we multiply 7 by 4 to get 28. 7 times 2 is 14, plus 2, 16. And now we move to the next digit, which is a 1. We multiply 1 by 4 and then 1 by 2, and then we push the digits back over 1 column because the 1 is not actually a 1, it's a 10. Okay, 1 4 is 4, 1 2 is 2. We add to get 408. Now, the quick way to find the final answer is to argue that you start with 4 decimal digits in total. 17 doesn't have any. And so you should end with 4 decimal digits. You can put a 0 before the 4 and then the decimal point to end up with 0.0408. And the long way to argue through it is to say that in going from 0.0024 to 24, the number became 10,000 times larger. In going from 17 to 17, of course, the size of the number did not change. And so the answer that we get will be 10,000 times larger than what we are seeking. And to make it 10,000 times smaller, we move the decimal point back over 4 digits. And we end up with 0.0408. Now, two kinds of multiplication for which you should know shortcuts. If you multiply by 10, 100, 1000, and so on, count the number of zeros that you're dealing with and move the decimal point to the right over as many digits. We did discuss the reason why this works, and of course when you multiply by 100 and you move the decimal point forward over 2 digits, you reassign the value of each of the digits. 4, which was in the ones, is now in the hundreds. 5, so that makes it 100 times larger, from ones to hundreds. In fact, here it's just a 4, whereas here it's actually a 400. 5, which was in the tens, is now in the tens, and it became 100 times larger. And same for 2 and 3. And so the total value of these digits will also become 100 times larger. Number 2, 3.2 times 1000, we move the decimal point over 3 digits to the right, and we add zeros if we have to, and we get 3200. Okay, the next thing to know is multiplication by subpowers of 10, such as 1/10th, 100th, 1000th, and so on. And in this case, you count the number of decimal digits in the number that you're dealing with. If it's 0.1, there is 1 decimal digit. 0.01, there are 2 decimal digits. In 0.001, there are 3 decimal digits. And then you move the decimal point to the left over as many digits. So as an example of that, 0.1 times 42.5, there is 1 decimal digit in 0.1. We move the decimal point back over 1 digit, and we get 4.25. To explain why it is that the decimal point moves back over 1 digit, I'm going to rely for now on the semantics of what it means when we multiply a decimal number such as 0.1, 0.01, 0.001 by another. We'll find out later on that multiplication, when it comes after either a fraction or a decimal or a percent, can be read as of, and therefore we can read this as 1/10 of 42.5. So of course the formal reading of 0.1 is 1/10, and if we go by the formal reading, it makes a lot of sense now. 1/10 of 42.5. And if you think about it, 1/10 of a value is the same as dividing it by 10 if you want to find 1/10 of a value. And so because we need to find divide this by 10, decimal point moves back over 1 digit. Number 2, 0.01 times 783.1, and the formal way of reading it is 100th of 783.1. 100th of implies that we divide by 100, and therefore decimal point moves back over 2 digits, and we get 7.831. Back to 1/10 of a value. 1/10 of 275 means 275 divided by 10. Decimal point moves back over 1 digit, and we get 27.5. And 1,000th of 3.15 means 3.15 divided by 1,000. Decimal point moves back over 3 digits, and we add zeros if we have to, and we get 0.00315. All right, so that's multiplication, and now we can move on to division. Okay, division. And for this one, we need to talk about equivalent divisions. And this has to do with the fact that when you have a division, if you multiply both the dividend and also the divisor by the same number, the answer will not change. As an example of this, 8 divided by 2 is 4. And if I multiply both 8 and 2 by, let's say, 10 and divide them, I still get 4. I could multiply the value of 8 and 2, both of them, by 100. And then if I divided those, I would still get 4. Now, it doesn't have to be 10 or 100 or 1000 and so on. Although here, with the division algorithm, those are the ones that we care about. It could be that you multiply 8 and 2, let's say, by 3. And you get 24 divided by 6. And the answer is still 4. Okay, this is actually a very important thing to know. In case you didn't know this, you should know it, and you should never forget this. This kind of understanding comes in every now and then in when you solve problems, and that figures big time in the division algorithm. And that's what we have next, the division algorithm. Now, there are 4 steps that I'm going to list, actually 2 steps that I'm going to list, and then we will talk about them in more detail. Step 1, which is a preparatory step, is to get rid of any decimal digits that you may have in the divisor, and I'll tell you how it's done through examples. The reason for this is because step number 2 assumes that the divisor does not have a decimal, it does not have any decimal digits. And then in step number 2, of course, you can work out the sign first, and then you basically follow the algorithm for the division of natural numbers. 2 things to keep in mind. One is that you must deal with the whole side first before you even touch the fractional side. And number 2, before you pull down the first decimal digit, that's the first digit on the right side of the decimal point, you should put the decimal point at the top. In case you run out of digits and the remainder is not 0, you can always add a 0 and pull it down and continue with the division until you either get a remainder of 0 or you find a repeating pattern. Alright, let's begin with step number 1 and focus on that step for a bit. As I mentioned, step number 2 requires that the divisor, which is the number that you divide by, should not have a decimal, should not have any decimal digits. And the job of step number 1 is to get rid of any kinds of any such decimal digits in the divisor. And so let's see how we can do that. Example number 1, we have 4.14 divided by 0.3, and right now the problem that we have is with 0.3. The dividend doesn't matter whether it has a decimal point or not. The division algorithm step number 2 will work whether the dividend has a decimal digit, has decimal digits or not. It's with the divisor that we have an issue, and if we have decimal digits, which in this case we do, digit 3, then we need to get rid of those. Now, to do that, what we can do is we can take the decimal point here and move it to the end. That would be the same as multiplying 0.3 by 10. And so, because we just mentioned that, if you remember, we just mentioned that in a division you can multiply both the dividend and the divisor by the same number, and the result of the division will not change. If we move the decimal point in 3 over 1, which is over 1 digit, which is the same as multiplying by 10, then we have to do the same to 4.14 so that the result of the division does not change. And therefore we multiply 4.14 by 10 as well, which moves the decimal point over 1 digit as well. Basically, if you move the decimal point over the same number of digits, like over 1 digit or 2 digits or 3 digits, in both the dividend and the divisor, then you're multiplying both of them by 10, or you're multiplying both of them by 100 or 1000, and so the result of the division will not change. And therefore now we modify the division from 4.14 divided by 0.3 to 41.4 divided by 3. And because both the dividend and the divisor have been multiplied by 10, the result of the division that we get for 41.4 divided by 3 will be the same as the result of the division for 4.14 divided by 0.3. Problem number 2, this one we don't have to take the preparatory step because the divisor doesn't have any decimal digits. Number 3, same. The divisor, which is 2, does not have any decimal digits. Number 4, again, we have a divisor that has no decimal digits, and therefore we don't have to take the preparatory step. Number 5, now we have a bit of a problem because the divisor has decimal digits, in fact 2 of them. And so we can get rid of them by moving the decimal point forward over 2 digits, which is the same as multiplying by 100. We multiply 1.008 by 100 as well, which moves the decimal point forward over 2 digits. So move the decimal point in the divisor to the end. Find how many digits you move the decimal point over, in this case 2. Do the same with the dividend. Move the decimal point over 2 digits to the right. Our new division then is 100.8 divided by 2, and now the divisor doesn't have any decimal digits. And because we moved the decimal point over the same number of digits in both the divisor and the dividend over 2 digits, both of them got multiplied by 100, and the result of the division will not change. And the last example, 7.5 divided by 0.015. Now we have 3 decimal digits. We move the decimal point forward over 3 in the divisor to get 15. And then we move the decimal point in the dividend over 3 digits as well to get 7,500. Alright, so that's how step 1 works. Now let's go to step number 2, and let's say for problem number 1, now that we've moved the decimal point so that the divisor doesn't have any decimal digits, we are going to carry out 41.4 divided by 3, and whatever we get for this division will be the same as the division 4.14 divided by 0.3. Okay, we set up the division. On the right side we have it, 41.4 divided by 3. Now you have to make sure that you always work with the whole side before you even touch the decimal point or digits on the right side. And when it comes to working with this division, we start with 4 here. 3 into 4 goes once. 1 times 3 is 3. We subtract to get 1. Okay, now 1 digit comes down, as always. And remember that every time a digit comes down, we have to answer the question, how many 3's fit into the number that we have? How many 3's into 11? 3 of them. 3 times 3 is 9. Subtract to get 2. Now comes the next thing you have to keep an eye on. Before you pull down the first decimal digit, you put the decimal point at the top. We put the decimal point at the top. 4 comes down. And now how many 3's into 24? Keep in mind, you do not pull the decimal point down. 3 into 24 goes 8 times. 8 times 3 is 24, and we subtract to get 0. And we're done. So the answer to problem 1 is 13.8, and the answer to both of these divisions is 13.8. Let's move on to problem number 2. Now we have 1.1, and we want to divide that by 40. As usual, we have to focus on the whole side first. We have to do that side, even if it gives us a 0. We have to write something on the top for the whole side before we continue to the fractional side. So we have to answer the question, how many 40's fit into a 1? And the answer is 0. We write 0. 0 times 40 is 0. Subtract to get 1. Before we pull down the first decimal digit, decimal point goes to the top. And then 1 comes down. Now, every time a digit comes down, we have to answer the question, how many 40's fit into it? How many 40's into 11? The answer is 0. We write 0. 0 times 40 is 0. Subtract to get 11. Now, it appears that we have run out of digits, and the remainder is not 0. And in such a case, you can of course claim that 1.1, which says you have 1 unit and 1/10, you can put a 0 here and claim that you have 0 hundredths. And therefore, at this stage, we add a 0, pull it down. How many 40's into 110? The answer is 2 of them. 2 times 40 is 80. We subtract to get 30. Now we're going to add another 0 to indicate that we have 0 thousandths, and we pull it down. How many 40's into 300? 7 of them. 7 40's 280, subtract to get 20. Now you notice that the division is becoming a little bit long. And this can happen. So we add another 0 and put it down, and we get 40 into 200, 5 of them. 5 times 40 is 200. We write that down and then subtract to get 0. And now we're finally done because the remainder is 0. But you notice how long the division became. There is a shortcut that we can take. This shortcut is pretty useful, and if you by and large feel comfortable with long division, I recommend that you practice it in case you don't know it already. It's an amazing shortcut, and you will see that it pops up in many situations. So to explain how this shortcut works, I'm going to do the same division again, but this time I'm going to employ the shortcut. Alright, so let's do the setup again. 1.1 divided by 40. Now here as usual, we have to work out the whole side before we can move on to the fractional side. So we have to answer the question, how many 40s into 1? And the answer is 0. We write 0 down. However, what we will not do is we are not going to multiply 0 by 40, because we know it's going to give us 0. And then if we do 1 minus 0, we get the 1 back. We just continue with the algorithm. Decimal point goes to the top. And now we think of 11. 40 into 11, again 0 times. And again, I'm not going to do 0 times 40, 0 subtract, you get 11, because I get 11 back. I'm just going to add a 0. And then 40 into 110, 2 times. 2 times 40 is 80. And then we subtract to get 30. Now instead of adding a 0 here and pulling it down, I will just add a 0 right down here. And then 40 into 300, 7 times. 7 times 40 is 280. Subtract and you get 220. And then again, I'm not going to add a 0 at the top and put it down. I'm just going to put the 0 down here. So now we have 200. 40 into 200, 5 times. 5 times 40, 200. Subtract 0. And we're done. So as you can see, this is shorter and much nicer than the previous one. It's a kind of shorthand that I highly recommend. Again, especially to those of you who already feel comfortable with the long division algorithm. It takes a bit of practice to become good at it. And again, if you don't know it already, I highly recommend that you practice. When you have zeros, don't multiply and write it down and subtract. Just move on to the next step. All right, next we have, I actually think I removed the examples that I had. Let me see if I can bring them back. Okay, where were they? We were actually at the division algorithm, so maybe a bit farther ahead. Yeah, there we go. We talked about equivalent divisions, and then we had the examples. Okay, 4, 5, and then we had 6. Sorry about that. All right, we move on to the next division, which is 15 divided by 2. So 15 divided by 2. And keep in mind that the decimal point is on the right end of 15, because 15 is on the whole side. It's a whole number, so it should be on the whole side. So going digit by digit, now taking our time, 2 into 1 goes 0 times. 0 times 2 is 0. Subtract to get the 1 back. 1 digit comes down. 2 into 15, 7 times. 7 times 2 is 14 rather. Subtract to get 1. And now we have ran out of digits. But keep in mind there is a decimal point after 15. And so we can add it on and put it on the top. And then of course we can claim that we have 0 tenths and write down 0, pull it down. 2 into 10, 5 times. 5 times 2, 10. Subtract get 0. And we're done. Now I would like to present the shorthand for this division. Just keep in mind how long this has become. Owing to the fact that this 0 didn't even have to be written down to begin with, leading zeros are not going to change the answer. And then writing it down and then multiplying by 2, writing it down and subtracting to get the 1 back, all of this can be avoided. And the 0 here and the decimal point, I won't bother writing them down. I just put the decimal point at the top and put a 0 down here directly. So here's the shortcut for that division. See if you like it. 15 divided by 2. 2 into 1 doesn't fit. We'll move on to 15. 2 into 15, 7 times. 7 times 2, 14. Subtract 1. Now put the decimal point at the top, which is actually here too. Add a 0, pull it down. And I just pull it down. I'm not going to add the 0. And now 2 into 10 goes 5 times. 5 times 2 is 10, and we get 0. Okay, much shorter and much nicer. Number 4, we have 25.6 divided by 32. Now again, we have to work with the whole side, and let me take my time and do the division digit by digit. 32 into 2, 0 times. 0 times 32 is 0. Subtract to get 2. 1 digit comes down. 32 into 25, 0 times. 0 times 32 is 0. Subtract to get 25. Decimal point goes to the top. 6 comes down. 32 into 256, 8 times. 8 times 32 is 256. And then subtract, and you're done. So the answer is 0.8, and of course the leading 0, actually this one anyway, was not needed. Let's do the shortcut division. 25.6 divided by 32. On the whole side, 32 doesn't fit into 2, and therefore we move on to 25. 32 doesn't fit into 25, but we may not move to 256 because we have to deal with the whole side first. And so at this point we have to put a 0 down. I'm not going to do 0 times 32, 0 and subtract to get 25 back. Decimal point goes to the top. And now I move on to the next digit. 32 into 256, 8 times. 8 times 32 is 256, and we're done. That's pretty neat. Okay, the next two topics, division by 10, 100, 1000 and so on. Again, we do have a shortcut for these divisions. And as we discussed earlier, you count the number of zeros in 10, 100, 1000 and so on, depending on which one you're dealing with. And then you move the decimal point to the left over as many digits. Moving the decimal point to the left over 1 digit will make the number 10 times smaller. Over 2 digits will make it 100 times smaller, and so on. And again, this has to do with reassigning the values of the digits, and it has to do at the core of it, at the heart of it, it has to do with the fact that each place value is 10 times larger than the one on its right and 10 times smaller than the one on its left. Now, my apologies for repeating this all the time, over and over, whenever I get a chance, and I will continue to do so because I want you to remember it. It's such a key concept. It can be used to explain so much of the behavior of the decimals that I would like to, as I mentioned, make you as conscious of it as possible. Okay, so as examples, number 145.6 divided by 10, we move the decimal point back over 1 digit and we get 4.56. Number 2, 0.089 divided by 100. Decimal point moves back over 2 digits and we end up with 0.00089. Number 3, 920 divided by 1000. Now in 920, that's a whole number, so it should be on the whole side of the decimal point, which means the decimal point is on the right end, and it moves back over 3 digits to just before the 9. Now we do prefer to write a 0 before the decimal point in case the whole part is 0, And I won't take time off of this video, add on time to this video by explaining why. Other than the fact that its absence usually has led to issues, decimal point can be sort of missed, which makes your number at least 10 times larger. And in the section on measurement systems, we'll talk more about this. And the 0 at the end, if you're not dealing with any kind of significant digits in measured values, you can of course drop it and we get 0.92. Okay, the next topic is division by 1/10, 1/100th, 1,000th, and so on. So by sub-powers of 10. Now this is an interesting case because in such a case we sort of count the number of decimal digits in 0.1, 0.01 or 0.001 depending on which one you're dealing with. And then we move the decimal point to the right over as many digits. So your answer actually becomes larger. Let's talk about why that happens using an example. Okay, so if I have 43.89 divided by 0.1, there is only one decimal digit in 0.1, and we move the decimal point here forward over one digit to end up with 438.9. So to explain why that happens, how is it that you divide by 0.1 and the answer becomes larger? Let's take a look at the division 1 divided by 0.1. 1, of course, in the diagram has a length which is this much, and 0.1 has a length which is only this much. And 1 divided by 0.1 pretty much asks the question, how many tenths, how many pieces of this size fit into a 1, which is a piece that's that long? And you notice that 10 of them fit in. So the answer to this problem should be 10. And you notice that I did start with 1 and I ended with 10, a number that's larger, even though I divided. And you might be surprised by it. In case that's the case, my guess is that because when we are kids and they teach us how to divide, they begin with division by 2, 3, 4, 5, basically numbers that are larger than 1. And when you divide by a number that's larger than 1, the answer will be smaller than what you started with. But so I guess that's how in the back of our heads, in the back of our minds, we sort of end up believing that if you divide, the answer will be smaller than what you started with. However, if you divide by a number that's less than 1 in size, such as 1/10, the answer will be larger. And if you take a look at what we're talking about here, the semantics behind 1 divided by 0.1, which is basically how many tenths fit into a 1, how many pieces of this size fit into a 1, then it does make sense that the answer should be larger because that's a tiny piece. And so we get 10 of them. And in a similar way, if you try to find out how many tenths fit into a 2, the answer will be 20. There is 10 in 1, and then you end up with 20 in 2. And so I started with 2, but now I am ending with 20. Okay, the next problem, 719 divided by 0.01. And now here we have 2 decimal digits, and we move the decimal point in 719 forward over 2 digits, and we end up with 71,900. And of course it does make sense. How many hundreds? That's an extremely tiny piece. Fits into 719, the answer will be 71,900 of them will fit in. It should also be, it's important for me to actually mention as well that in these problems, you notice that you are dividing by 0.1 and dividing by 0.01. If you switch the order and put 0.1 divided by 43.89, then it doesn't work in this way, of course. You will have to do the long division to figure it out. So keep in mind that the subpowers of 10, such as 0.1, 0.01, and so on, they appear as divisors in these problems. Okay, problem number 3, 0.3 divided by 0.001. How many thousandths fit into 3 tenths? And we move the decimal point forward over 3 digits, corresponding to the 3 decimal digits in 0.001. And we need to add a couple of zeros to end up with 300. All right, so here's the third very important topic in this video that I would like you to remember. This kind of knowledge is sort of like what I call a micro skill. These are those tiny skills that people who are good in math have. You should know this. You should never forget this, and you should always use it when you get a chance. When you divide, if the divisor, the number you divide by, is greater than 1, the answer will be smaller than what you started with. Now, greater than 1 doesn't have to be 2, 3, 4, 5. It can be 1.1. It can be 20.38. As an example of this, 14 divided by 2 is 7. I'm dividing by a number that's greater than 1. And I end up with an answer that's less than what I started with. If the divisor is less than 1 in size, and this is all about size, by the way, the answer will be larger than what you started with. So 14 divided by 0.2, that's 2/10, which is less than 1 in size, will give me an answer which is larger than what I started with. How many 2/10 fit into 14? 70 of them. I'll let you work out the division. And of course, if the divisor is 1, you're dividing by 1, the answer will be the same as what you started with. So divisor greater than 1, answer less than what you started with. Divisor less than 1 in size, answer will be larger than what you started with. And if the divisor is 1, the answer will be the same as what you started with. Okay, last topic here on chain multiplication division of decimals. And in this case, we are talking about problems where we have, actually, let me get rid of this part. Okay, my apologies for that. I'll explain things through an example, and I have a lot more to say about this in the next video, which is on expressions. So here I will be short, and in the next video I will get into more detail about how it is that this what I'm going to tell you works. Let's say that you have chain multiplication division 24.2 times 20 divided by 2 times 2.3 divided by 2.5. And there are two ways to work this out, or two common ways anyways to work them out. One is suitable if you have a calculator in hand. Another is probably more suitable if you're working by hand, not on a calculator. On a calculator, of course, you go from left to right. 24.2, then you can multiply by 20, divide by 2, multiply by 2.3, divide by 2.5. You can do these in any order. You can start with 24.2 and then divide by 2.5, then divide by 2, then multiply by 20, and then multiply by 2.3. If you're working by hand, then the part that takes most time is the division part, and we would like to minimize that. And similar to the relationship that we had between addition and subtraction, where a whole bunch of subtractions can be turned into subtraction of the sum of them, here we can do the same. We can multiply the numbers that are being multiplied, such as 24.2, we have 1 times it, times 20, times 2.3, and then divide by the product of the ones that we are dividing by, like 2 and 2.5. That gives us, for the product here, 1113.2, and then divide by 2 times 2.5, which is 5. So this reduces the number of divisions to 1. Again, the top row would be suitable if you have a calculator in hand. The bottom one will likely be more suitable if you're working by hand. All right, so the final answer will be 222.64. Okay, everyone, this brings us to the end of this video, and thanks very much for watching. I wish you a great day or evening or night wherever you are, and I'll see you in the last video on expressions next. And for now, I will be gone in 3, 2, and 1.